Now in this video we are going to talk about simple cubic arrangement. This is the first arrangement in 3 dimension that we are going to discuss. The basic structure arises by packing the atoms in 3 dimension as follows. So the first layer that we create is the square pegging in 2 dimension that we had earlier created. If you make the second layer of atoms to sit right on the top of the first layer, the arrangement that you will get is going to be like this in this diagram. This particular shape that is created is called simple cubic. In this case, the parameters of crystal are going to be, all the sides are going to be equal, so A equal to B equal to C, and all the angles are going to be equal to 90 degrees. So alpha, beta and gamma, all of them are equal to 90 degrees. Now there are certain calculations that we are going to perform using this particular system. The first one is relationship between A and R, where A is the side of the cube and R is the radius of the atom. So you can easily see that the two atoms are going to touch each other. So this particular length, edge length of the cube is going to be equal to 2R. The second one is effective number of atoms, which is denoted by Z. Now in this case it is going to be 1 by 8, which is contribution by each corner atom into 8, because there are going to be 8 atoms at the corner of the cube. So that will give you effectively 1 atom per unit cell. The third parameter that we are going to calculate is called packing fraction. So in 2 dimension we had taken area occupied by the spheres upon area of the unit cell. Now in case of 3 dimension we are going to take it as volume occupied by the atoms upon volume of the unit cell. So now the volume occupied by the atom is going to be 4 upon 3 pi r cube, because there is only one effective atom. So we take volume of one sphere and divide it by volume of the unit cell, which is A cube. So the calculation will give you packing fraction as 0.52 or 52%. So that means that 52% of the space is occupied by the atoms and remaining 48% of the space in the unit cell is empty. The fourth parameter is called coordination number. It is defined as number of atoms touching any particular atom, and it is in this case equal to 6. You can just pause the video, think through why is it 6, and then resume the video. I will explain you how coordination number is 6 in this case. So let us take a reference point as this one. Now if this is your reference point, the atoms that are going to touch this particular atom are 3, 5 and 1, which belong to this particular unit cell. Now apart from that, the atoms from adjacent unit cell are also going to touching this particular atom. So this atom which is marked 6th in this case is going to be right besides this unit cell. Similarly 2 is going to be the atom which is directly on top of this atom, and 4 is going to be an atom which is just in front of this particular atom. So there are going to be 6 atoms which are going to be touching your particular reference point, which is this in this case. So that is why we say that coordination number in this case is equal to 6. Now the next analysis that we can do is neighbor analysis. Now let me explain you what we mean by neighbor analysis. So in this case what we are saying is we are going to find nearest neighbors to a particular point. So again you can take this as a reference point. So the nearest atoms which are present to this particular atom are at a distance A, which is this length, and there are 6 such neighbors which we just calculated. Similarly, the next nearest neighbors, which are going to be at a distance of A root 2, or basically this face diagonal atoms, and there are going to be 12 such atoms. The next raised to power 2 signifies next nearest neighbors. So neighbors which are going to be after this particular distance of A root 2. The next distance is basically a root 3, and similarly next 3 is going to be neighbors which are next nearest neighbors, so that are going to be at a distance of 2a, and there are 6 such neighbors. Now you can pause this video at this point, just try to figure out how we are getting these numbers, and then I'm going to explain you how exactly you can calculate these neighbors and how to visualize the atoms. Now I have drawn this particular diagram to explain you the neighbor analysis. So if you carefully observe the diagram, I have drawn 8 cubes. Now I'll make this as my reference point, and let us try to find out what are the atoms that are nearest to this particular atom. So as we had seen that the nearest atoms are at a distance of a, which is your edge length. So there are 6 atoms that I can show you in this diagram. So this is one of them, this is first, this is second, this is third, this is fourth, fifth and sixth. These are the 6 atoms which are marked in black that are going to be the closest to your particular central atom which we have taken as reference. These atoms are at a distance of a, and they are going to be touching each other. So this atom is going to be in touch with this one. This atom is also going to be touching this one. Similarly this is in front and this is in back. These are the 6 atoms which are going to touch your central atom. So that is why the nearest neighbor we get as 6. Now the next nearest neighbors are at a distance of a root 2, and there are 12 such neighbors. How do we get that? Just look at this particular atom again as a reference. Now there are 4 red dots that I have created in this horizontal plane. 1, 2, 3 and 4. These are going to be at a distance of a root 2 each. So this distance is a root 2 because this is phase diagonal. Similarly this also is a root 2 phase diagonal. This is also a root 2, and this is also again going to be a root 2. Similarly, if you look at this vertical plane, there are again 4 such red dots that we can get. So this particular distance is a root 2 again. This distance is also a root 2. Similarly this, and similarly this. So there are 4 such atoms in this vertical plane, and you are going to get 4 more red dots if you look at the front part of this particular plane. So this particular distances from this point are also going to be a root 2. So there are in total 12 points which are at a distance of a root 2 from your center atom or reference point. The next nearest neighbors were at a distance of a root 3, and there were 8 such atoms. So again, if you look at this diagram, all the green points that we have created are nothing but body diagonals, and they are going to be at a distance of a root 3, and there are such 8 body diagonals you can get because each atom is going to be part of 8 surrounding cubes, and each cube will have one body diagonal atom. So there are going to be 8 such atoms which are at a distance of a root 3. So all the green atoms are at a distance of a root 3, and there are such 8 atoms present. If you want to calculate next 3 or next nearest neighbors, those are going to be at a distance of 2a. So you can just imagine a point over here. Similarly a point in this side. One point above this and one point below this. One point in front of this and one point at the back of this. So there are again going to be 6 points which are at a distance of 2a from this central reference point. I hope this neighbor analysis is clear to you. This is very important because there can be various questions that can be formed using this analysis, and we are going to do similar kind of analysis for other 3-dimensional structures also. So just review this section very well and try to prepare this diagram yourself.